everybody, it's Wrangler here, and you may have been forgiven for believing that I've fallen off the face of the planet because I haven't been doing many videos lately, but I haven't been idle. I've been spending all of that time since the last video working pretty hard on programming the DSP, the digital signal processor chip. In this machine we're looking at here, the AA3000 Plus in an Amiga 3000 case. There it is, happily doing Mandelbrots. But before we talk a little bit more about programming the DSP chip, let's do a quick recap and go back in time to 1990, when this machine, the Amiga 3000, had just come out as the latest and greatest in the line, and it featured this CPU, the 68030, running at 25 megahertz, which was the king of the Motorola CPU line at the time. It was accompanied by this chip, the floating point unit, the 68882, also at a staggering 25 megahertz. And once that machine had come out, thoughts began to turn in the Amiga development department at Commodore to what came next, and the idea was a project that was codenamed the Amiga A3000 Plus. It was seen as a development and evolution of the A3000 using the same CPU and FPU, but this time with the new Pandora chipset, which eventually became the AA and ultimately AGA chipset. But it also had a network chip designed into it and the digital signal processor chip. The first working version of that motherboard was produced in February 1991 and then worked through a few revisions, but production quality issues meant that it never came into being, and actually development started again from the revision 0 version of the A3000 Plus motherboard, with some of the goodies stripped out. Now known as the AA3000, it's essentially an A3000 with the AA chipset and that digital signal processing chip still retained. In the end though, Commodore gets new management and they sweep through the organisation, killing all existing projects, including the AA3000, which never goes into production. Instead, in 1992, we get this machine, the A4000, which does feature the AA, now the AGA chipset, but it has an IDE disk interface instead of the faster SCSI interface, and no DSP chip. And so neither of those true successors, you might call them, to the A3000 ever come into being until, that is, 2019, when a user called Hesse on the website Amiga recreates a modern version of the AA3000 and calls it the AA3000 Plus, because it's not an entirely exact replica of the original board. For example, it has SIM slots for memory instead of accepting individual chips, and it has a modern flicker fixer. Now, I have been asked 1 million times, where do I get one of these AA3000 Plus motherboards from? So here is the answer to that question. Here is the link to the sales thread on Amiga, the one website where you can state interest and pay Hesse for a motherboard and get one of your own. I shall just say in passing, by the way, I have no connection to Hesse or his creation of the motherboard, apart from being a very happy user. So that's the backstory, and it brings us up to date. We have here an Amiga with an extra chip in it, the DSP chip, and then we get to how about programming that chip and producing Mandelbrots like the ones we're looking at on the screen here. That's what I'm going to cover now. So here is the source code from the Mandel program that I wrote back in February 2021. It's a standard C program. You can see some of the include statements here, and there's more C further down, doing all of the work that's required to color each pixel on the screen according to the Mandelbrot algorithm. Pretty standard stuff. and nothing unusual about that. What is unusual is the bit that I skipped over, which is here, which is the code for the DSP to do its job, bearing in mind that's an entirely separate chip running its own program. And here is that program that we can see on the screen. Pretty terrible programming really to have embedded the DSP routine right in the middle of a C program for the CPU. That's one problem, but it's worse than that. All of the instructions you can see here in green on the right hand side, such as this R3 equals instruction and then a NOP, all of those are in fact comments and actually need inserting by hand what the correct machine code instruction is, which is the hexadecimal figures on the left hand side. So yes, it does mean every time you change the program or insert a new instruction, you have to work out what the new hexadecimal machine code equivalent is. And by the way, if you're inserting that in the middle of a loop, for example, then that can change how far the loop has to jump backwards or forwards through the program. So other instructions can change as well when you start inserting new bits of code. It really is very, very painful to program in this way. Actually, programming the Mandelbrot generator here wasn't quite so bad as it sounds, because I was able to borrow the source code for a program called Artabrot, produced by George T. Warner for one of the Mac Quadra computers that had the same DSP chip within it. So I was able to lean on that pretty heavily, but nevertheless there were some functions that I needed to write for myself and come up with the individual machine code equivalents. It was painful. So that approach to coding up the DSP really isn't very sustainable if you're going to write anything more complicated. So how should you do it? Well, let's have a look at this. You can see I've got on the screen here a .s file, in other words one that is just assembly language, and this is just assembly language for the DSP itself. So you can see we've got the kind of R12 equals R0 register allocation instruction here. None of those hexadecimal machine code conversions done yet, just the assembly language versions. I mean, just before we look at converting this into machine code, the other thing we could do is some of these sort of global expressions up the top here, which really are just identifying bits of data that we'll want to reference in other bits of the program. And instead, in the earlier version we were looking at, I had to work all of those out by hand. Here we're just declaring them as labels that need to get evaluated later on by the machine itself, and that takes a lot of stress and strain off the programmer if that's all sorted out automatically by just declaring them as global variables, which is what this section of code's doing here. So we can look through all of that. Here are those data points later on that will just get referenced by other bits of program, and in fact all of this Mandel.s program is doing is just the Mandelbrot algorithm. So all very interesting, but you know, how do we turn that into machine code? Let me just come over here where I'm in Cygwin 64. This is just a really convenient way of being able to access effectively Linux, 64-bit Linux via Windows using Cygwin. Maybe not exactly the fastest way on earth to run Linux, but actually very convenient because I can swap files very, very easily, click and drag between Linux and Windows. So, you know, what did I do to try and make the life of the DSP programmer easier? Well, I wrote an assembler. So let's just have a quick look at that. It's called ASM3210, so just mirroring the name of the chip. So there we go, there's the version message from ASM, and what we can do is assemble the program we were just looking at there. So let's do that, and if I turn on the L switch, what it's going to do here is just open up a listing file. So let's come back to here, so we can see all of the assembly language on the right here, but then the assembler itself has converted to machine code, which is exactly what we want an assembler to do. It's done all the heavy lifting for us, including working out all the loops and things like that, so makes life significantly easier. The other thing I'm able to do using an assembler actually is to split up the DSP code. So what we were looking at before was the Mandelbrot algorithm alone, but I also need some setup code for the DSP chip, which is in a separate file here. This is all the setup code that we're looking at that just gets the DSP chip going, if you like. Again, I can make use of global labels, so I don't need to work out all those references and have that in an entirely separate file. So, you know, once I'm happy with that, I can just forget about it and focus on the actual algorithm I want the DSP to do, which might be Mandelbrots, might be something else. So again, that is a labor-saving device. So we've got an assembler that produces the machine code from the assembly language for the DSP, and that is a major step forward, but that's not quite the end of the story. Let's just go back to our view here of the various different files where I've split up the original Mandel DSP code, because we've got some other routines here, some of which are designed for the 68000 series CPU, such as these first couple of files here, and Mandel M68k.c here. Let's just take a quick look at that and open that up. So we were looking at some of this code before, all the include files, and this is what programs the 68000 CPU to actually run the Mandelbrots and color each of the pixels on the screen. So nothing very exciting to talk about there, except that we now have a number of files that we need to convert from C to assembler and from assembler into binaries. These object files, the .o files, that is pretty standard stuff for programmers to have these various files and converting them into object files and then linking them all together. In other words, converting those into a single binary and resolving all of the cross-references, you might call them, between the various different files. That's pretty standard stuff, and there are linker programs that do all of that for you, so that wasn't something I had to focus on. There was one particular aspect though that makes this quite tricky for the programming the DSP chip, and that's the fact that references in the DSP have to be handled in a particular way. So what do I mean here? Well, you can see, let's find a reference to an absolute value, and perhaps here is the easiest way to do that. You can see we've got something called DSP code start, the start of the program. The fact is that is going to end up being a location somewhere in the Amiga's memory, and we can't know in advance where that's going to be. In other words, when we load this final file that we're ending up with, the Amiga operating system might put it anywhere at all. We can't know in advance where that's going to be, and that means DSP code start will be some, you know, semi-random 32-bit absolute value. And the way operating systems, and certainly Amiga OS, handle all of this is just simply to keep a track record, a log of all of these different labels, and just say these need to be resolved at the time the program is loaded by the operating system and begun. These are called relocations. Now, Amiga OS handles all of that for regular 68000 series programs, not a problem. The difficulty comes with the fact that we're using a different chip here. We're trying to program the DSP chip with a 32-bit value, and actually there is no instruction for the DSP that does that in a single instruction. This R2 equals DSP underscore code start will actually be turned by the assembler automatically into two instructions, loading the two halves of the 32-bit instruction. In other words, the upper 16 bits and the lower 16 bits will be done in two separate instructions and split in that way. And unfortunately, the standard Amiga OS way of doing relocations to any address do not handle versions where you have to split it into two 16-bit halves. That simply wasn't foreseen by the programmers of Amiga OS. So we're left with a bit of a problem. You know, how do we handle all of that? And actually, it took quite some effort to work this all through. Now, the way I approached all of this was the fact that the output from the assembler is produced in something called the ELF format, not the standard Amiga hunk format. And the reason I did that was because ELF does allow for these two instruction relocations of 32-bit values by effectively pretending that the DSP 3210 chip is in fact a PowerPC processor where these split relocations are quite a normal thing. So ELF, by relying on the ELF format as the output from the assembler, the ELF format just automatically enables me to handle these relocations. The problem is Amiga OS won't allow me to load an ELF format file. So I can create all the object files, I can link them all together into a single one, a single ELF file at the end of that process, but then I need to convert that into something that Amiga OS can handle. So I had to create another program called ELF to exe M68K, which allows the conversion of that ELF file into something that the 68000 series processor and Amiga OS in particular can handle and just run. So there's an extra program that comes with the package for ASM3210, which is ELF to exe M68K, just to enable that final step to create what we really want, which is an executable. So if we come back to Cygwin, then what we can do is a simple make instruction, and that is going to go away and compile each of the C programs into the object files. You can see the .o files being created here, then link it all together, use the assembler program to assemble the DSP assembly language program into object files, link all of those together, and then finally use the ELF to exe M68K program to create our final Mandel DSP exe file. It sounds really complicated. Actually, the point is it isn't. All of this make file is done automatically for you. The crucial bit is the programmer can simply focus on programming the DSP chip in assembly language, and then all of these complex instructions are just done in the background to create the executable. So that's an assembler for the DSP chip and the associated programs with it. You might think of them as the low-level tools, and they certainly take a lot of strain off the programmer. But I guess the real question is, can we go a bit further? I mean, assembly language is all very good, but it does mean learning a whole new language. It gives you the ultimate control over what the chip is doing, and so the most power, because you can state each and every instruction for the chip to perform. But it does carry some disadvantages with it, including the fact that there are certain instructions that on the DSP chip cannot run consecutively. In fact, you have to wait for the outcome of the instruction to be fully reflected in the chip before you can use the results of it, a so-called latency that you have to take into account with some of the instructions. You can see up here, after I've set the R3 register value to a particular address, I can't actually use that address in the next instruction, so I have to insert a no operation, a NOP instruction in between to wait for that register to be ready to be used, if you like. Now you can handle all that by hand, but it is all quite challenging to get your head around the number of NOPs that you need in certain situations. So actually using the assembler helpful if you want complete control and power, but not altogether the easiest thing for humans to use. The question is, can we do any better? So my answer to that question is yes. Let's just take a quick look at that. The next highest level language that you might want to use for any given situation is C, and here is an example of a quick C program for the DSP. Why C? Well, the fact is, first of all, it's easy, relatively easy to convert that into assembler. Secondly, it's a widely used language, so actually porting code from one chip to another becomes that little bit easier if you can support the C language. So what we're looking at here is a very simple program that is going to do some basic arithmetic functions, and let's just have a quick look at this particular one here. What it's going to do is to take two individual values, a and b, and return a divided by b as an integer value. Oops, let me expand that back again, as an integer value, and down here we've got the floating point equivalent, so two floating point values, a and b, and return the division between the two. Why am I particularly calling out those two? Well, division is not something that the DSP chip can do natively in its own internal instructions, so to speak. So the divide function, whether you're dividing that as two whole numbers, integers, or floating points, has to be simulated, emulated by several instructions on the chip. But once that's done, from the C programmer point of view, actually I don't care, and I can simply do divisions in the usual way, a divided by b. I don't really care how the chip sorts that out for itself. That is the advantage of having a C compiler. So what I've done is to convert the very well-known and used GCC compiler for the DSP chip. So let me show you that in operation by compiling this C program to produce the equivalent machine language, assembly language version. So let's come to that here. Here's my C program, here are my compiler executables, and what I can do is simply get that to compile via the following command line entries in Cygwin. And here's my .s file, which is the assembly language version of that, and that's what it looks like. So it has completely converted my routines, and let's just scroll down a bit. Here's the one to do signed division. It's completely converted that into these functions, and then I could call those from my program. So then what I can do is assemble, using the assembler, this assembly language program and functions, and use them in the rest of my program. In fact, that's what we'll look at in a minute. But it can't have escaped your attention that I'm running this all in a Windows XP virtual machine, and you might be wondering, why on earth are you doing that? The answer to that is a technical challenge that I've encountered. So what I would really like to do is have a version of GCC that can run on my 64-bit Windows machine, 64-bit Cygwin, but still compile 32-bit output, because that's what the chip, the DSP chip, is supporting. Unfortunately, although when GCC versions 4 and above handle that difference, the host machine being 64-bit and the target being 32-bit, actually I could not get that to work. Every time I tried, I got internal compiler errors, so I had to go back to GCC version 3, which only sort of expects a world of 32-bit, and run that in a 32-bit Windows XP virtual machine that you can see here to compile the code. The reason I'm saying all that is it's a bit of a faff. You can't do it all in one go, but if you're running a virtual machine, it's not too difficult to copy across the C files and assemble them to S files and then move them back to your regular 64-bit machine and carry on with them there. However, if anyone who is watching this knows what changed between GCC 3 and GCC 4 and above that broke the compiler setup, please let me know, because it would be good to fix this if possible. So we could take that file here, copy that, and bring that back into my main file here, where I've got all the 64-bit results. That's better. Got that as an S file now, and we can look at that in Visual C. That's the same program that we had before, and now I can carry on and compile all of that. So why don't we have a look at that? Let me just minimize some of this stuff and we'll do that. So I'm now back at my Sigwin64 command prompt. I'm now out of the virtual machine, back in Windows 10, and there is my assembly language version of the C program. Let's just turn that into an executable. Again, it's the make function, does all the hard work, and I've got my test dsp.exe file, which I am going to shove onto a USB stick, and from that we can test that out on the AA3000 Plus itself. So here I am back at the AA3000 Plus, and you can see that I am already in Workbench, ready to go. Here's my USB stick that I'm going to stick in the back, which has the program on it, and we will see what it comes up with. So there is desktop. Now let's insert the old USB stick. There we go. And open up the old command prompt. Execute that file. There we go. So I must have left in this top line from previous stuff, but the second line there, 1900 divided by -13, just check out the sign. Sign division, I get -146 in round numbers. I'm sure there's a fraction there. And what do I get when I divide 3.1415 by 35.2345? The answer is 0.0891. So there we are. C program running on the DSP chip. You know, right back to the start, why am I doing all of this? The idea is to make it easier to program for the chip inside this machine. If you don't have the tools there to do that, that really is pretty painful, as I showed at the start. If you want to get hold of the assembler or GCC for the DSP chip in the AA3000 Plus, the way to do it is to go to AmiNet. Both packages are on there. Search for ASM 3210 and GCC 3210, and everything that I've been showing you is available there. Please do download those packages. I really want to see something more interesting than Mandelbrots being developed for the DSP chip. So over to all the programmers in the world, please pick up from here and use the tools to come up with something exciting. So what might that something exciting actually look like? Well, the documentation for the A3000 Plus indicated that it was originally intended that the DSP chip would be used to provide significantly enhanced audio capabilities for the Amiga, including stereo 16-bit sound at CD quality frequencies. The design also even included a telephone line connection, so the Amiga could be connected up to the phone line with the DSP able to act as a fax modem, would you believe it? But other applications could include JPEG decompression and even MP3 decoding. Now I can tell what you're probably thinking right now, which is stop talking at me and show me some of the good stuff, the applications running on the DSP. I would love to. The fact is though, I've spent pretty much all my spare time over the last year developing the programming tools for the Amiga, so I don't have you any applications to show just yet on this machine. So if we're going to actually turn to look at working applications, we need to pick a machine that has always had a DSP in it from the day it launched. So enter the machine we're looking at here, the Atari Falcon. The Falcon was released in 1992, so a similar time to when the Amiga A4000 was launched as the high-end Atari ST, but it was discontinued pretty soon, in fact in 1993, and therefore is the last home computer that Atari ever produced. On paper, the specs are quite similar to the A3000 machine, relying on the 68030 CPU, running, it must be said, at 16 MHz, but also coupled with the 68881 or 68882 FPU. So similar CPU and FPU combination, but it was limited by design to only make use of a 16-bit data bus and 24-bit address bus, whereas the A3000 and the AA3000 for that matter would have been 32-bit throughout. What it does have in it, the Falcon, is the Motorola 56001 DSP running at 32 MHz. So yes, one of those DSP chips, but a different one to the one that had been chosen for the A3000 Plus and the AA3000. So you might ask, well, how do these two DSP chips compare? Actually, on paper it's really quite difficult to say. The Atari's 56001 ran at 32 MHz and delivered 16 MIPS, million instructions per second. It had on board 1024 24-bit words of RAM. The DSP 3210 that ran in the Amiga had a clock speed of 50 MHz but delivered 12.5 MIPS. So a little bit slower than the Atari's chip. It did have, however, 8K of RAM on board, which works out as twice as much, and that's fully 32-bit usable. So it's actually really quite difficult to say which is the more capable DSP chip, and so I'm going to call that a score draw, but probably on paper the A3000 would in fact be faster than the Falcon, simply because of the higher clock speed for the CPU and FPU and it having a full 32-bit wide data bus. Alright, so that's enough about the specs of the Atari Falcon. The question is, what can it do? And the answer to that is really quite a lot that there isn't time to go into on this video. And anyway, this is not supposed to be a head-to-head between the Falcon and the A3000. What I want to show you though is one particular application that has been written on the Atari Falcon, which really demonstrates what you can do if you are clever about the way you use the DSP chip on the machine. And what better to show you than a game? And what we're going to look at is Bad Mood. What is Bad Mood? Well, it is an enhanced version of Ultimate Doom written specifically for the Atari Falcon, and at least enhanced by a user called DML. I must confess, I don't know if other people started off the project. If you did, apologies for not naming you. Anyway, it is an engine that is there to run Doom WADs. It is not a conversion, by the way, of the PC code, rewritten from scratch as I understand it, but to produce the same output. Importantly, DML worked very hard to ensure a really good integration of those three chips on the Atari Falcon: the 68030 CPU, the FPU, but also the DSP chip. And there's a thread on the forum that I'll send a link to. This is on the atariforum.com that goes into quite a lot of detail about the technical aspects of getting Bad Mood to work, and in particular making best use of the 3 chips that I mentioned, so they're all doing tasks simultaneously to produce the overall end result. So I'm just going to do a quick cut here and then go straight into the game, show you what it's like playing one of the levels of Bad Mood. Just remember, this is running on a 16 MHz 68030 with FPU and DSP. Let's see what it looks like. So there's a bit of screen tearing going on, but I think that is primarily due to the way I'm capturing the Atari's video output. It certainly looks a lot less than that on the actual monitor. Overall though, I think you can see this is a really playable game on the Falcon, which I think is just a massive credit to the programmers who've worked on this. Fantastic job. Difficult to compare it with other versions of Doom. There's no frame counter that I've come across just yet, but either way, it just shows you the power of being able to use the DSP chip, because the 68030 with FPU on its own never would have been able to produce something like this. So there is hope for the Amiga with the DSP chip in it, that someone could do something similar for the AA3000 Plus. That's it for this video. Hope you've enjoyed it. See you again next time.